and thank you to all the organizers for the opportunity to present my work today. So this presentation is based on the anonymous paper that we put out approximately a month ago on arXiv. And this is a collaboration that we have with people in Bologna, in Cambridge, and Czech Republic. And in order to present this talk, I would like to divide it in basically five points. So first of all, I would like to give you a brief motivation of the problem of embedded inflation in UV theory. And we'll see that in order to do that, we need to also take care of modular stabilization at late times. So then we will come back to the case of inflation from string theory once we know how to stabilize moduli, how to implement also inflation. And finally, I would like to give you a brief summary of all the procedure that we did and the future work that we're gonna do after this work. So just with a brief motivation, as I mentioned, I would like just we all know that inflation is currently the standard realization of the early universe cosmology. And in this framework, we have different kind of potentials that are favored experimentally. Yes, so these are concave potentials in which the first one, for example, that we can see on the left-hand side corresponds to what is called the inverse power law inflation potential. And on the right-hand side, we have the exponentially decaying potential. Interestingly, the potential on the right-hand side, the exponentially decaying potential, was analyzed in several string theory models. So one example is the fiber inflation. And interestingly as well is the case of inverse power inflation potential that first appeared in the brane-antibrane potential or brane-antibrane system. However, this appeared without modular stabilization, and this is one of the keys of this work. So just like to put everyone in context, I would like to introduce you very roughly what brane-antibrane inflation means. And it's basically, we will consider a system of a brane and anti-brane, which are going to be separated by a certain distance, and this distance will correspond to the inflaton modulus. So when the D3 brane is going to move toward the D3 brane, this is what is going to actually generate inflation. And just coming back again to the case that I mentioned that this was done without modular stabilization. Then some years later, KKL-MMT analyzed the potential now, analyze the problem now, but it considered now a stabilization mechanism for the volume modulus. However, this mechanism, which was basically based in KKLT, they use non-perturbative corrections in order to stabilize the volume modulus. However, even though they managed to solve the problem of the volume modulization, they encounter now the generic eta-problem in which now this low roll parameter becomes large. So in the end, inflation is not realized. Subsequently, they managed to find that this can be cured as well. However, the form of the potential now would change. Now they didn't have this inverse power law potential, and instead we found what is called the inflection point potential, which is now experimentally ruled out. So based on all these problems, but also all these things that have been done in the past, what we managed to do in this work was to study or to provide a new example within string theory of an inflation potential, an inverse power law inflation potential that now considers also the volume modulus stabilized, but instead of relying on non-perturbative corrections or non-perturbative effects, we only rely on pure perturbative effects to stabilize the volume modulus, because we will see that this is precisely the key, that the fact that they use non-perturbative corrections to stabilize the volume modulus is what generates at some point the eta problem. So speaking about perturbative corrections and moving to the modulus stabilization topic, I would like you to briefly mention what are the perturbative corrections that are known so far, which we consider all of them in our study. So basically, we can go through them just by different orders in an alpha prime expansion. So at first order or at alpha prime order, there are no corrections known at this order. Then we can move to alpha prime square corrections, and in this case, we find corrections, but these corrections are not in the end, they are going to vanish because they also are gifted with an extended non-scale structure. However, what we can find also is a one-loop logarithmic definition that in the end is going to change the scalar potential and that appear in terms of this alpha. We will see later what this alpha means or where it can come from. But okay, so that's what happens at alpha prime square. Then moving on towards alpha prime cube, we have here like several corrections, which we can classify into different kind of corrections. First one is scalar corrections. And here we have also several corrections that are worth to go through in a more careful way. So the first one that appears here, that is proportional to psi, comes from an n equals 2 correction, and is the correction that was used, for example, in LBS. This is a well-known correction, sometimes called BBHL correction. Then we also have this correction that also appears at n equals 2, and it usually comes together with this other term that appears here as a logarithm of tau. However, this term, the one in the purple box, is only appears when you have high curvature in the extra dimensions. And finally, we have a combinatorial factor coming as well, which is usually of the order of 10 to the minus 3, 10 to the minus 4. And it is known only for the case of a single modulus. However, it is expected that it's also going to be a small number in the case in which you have more Kähler moduli. So the other kind of corrections that we have are non-Kähler corrections. And these are corrections that appear directly into the scalar potential as f to the 4 term corrections. And they scale as 1 over tau to the 11 over 2. And again, as I mentioned, this T3 just on a small number, it's a topological quantity that appears. And finally, the next order in the alpha prime expansion would be alpha prime to the 4. And at the order of n equals 2 and gs squared, we have this kind of corrections, where here in this case, C4 is a function of the complex structure moduli. And yes, these are the corrections, all the corrections that are known so far that we consider in our study. However, what we gonna do now is consider the leading order corrections. We will see that the other corrections in the end are gonna be present, but they will not affect the results of our analysis. So far, let's consider just the leading order contributions, which, as you can see, we have the logarithmic redefinition here, and we also have the BBHL term plus this enhanced logarithmic correction. So as it's usual to stabilize complex structure moduli, we will consider that the dilaton and these complex structure moduli are gonna be fixed at tree level by 3 form fluxes, which in the end are gonna induce a superpotential that we call W0. So this is standard procedure for the actual dilaton moduli. Sorry, the dilaton and the complex structure moduli. And so we will break the non-scale structure by adding these corrections, these perturbative corrections, that in the end are going to generate this scalar potential. So we can see that we have basically two cases. We can only have the case in which this alpha is 0 and psi is also positive. Psi is positive. And in this case, what we found is that we can get an anti-de Sitter minimum, this exponentially large volume. and a very small coupling constant. And in the other case, in which alpha is greater than 0 and small, as is expected in one loop corrections, we can get that this factor that is proportional to alpha here is going to act as an uplifting to Minkowski or the zeta, in which the minimum and maximum are going to be given by these expressions, which is, well, this WK that appears here is with K going from 0, -1, are just the 0 and -1 branches of the Lambert function. So just as an important note here is that we found that in order to obtain the zeta from this expression that we have here, we need to set theta in this interval smaller than 1, but larger than 0.9993. So also just it's probably worth mentioning that also in the case in which alpha is equal 0, we can still get the zeta minimum by introducing, let's say, another anti-brane in a different throat, different to the one that we are using for inflation, or we can also consider non-perturbative effects. However, this is not what we were looking for, because I mentioned that we were focused only in perturbative effects. And also we are like trying to get the simplest model that we can have. So we are just considering the simplest model, in which case it's just a single warp throat and just and pure perturbative effects. So what we did then is, okay, let's consider now a certain values for psi that from the Kreuzschlag database, we know that the ones that are favored are with psi in the range of 0.1 and 1.5. So we're going to fix this value, considering this value for psi, and then we find theta very close to 1. And also this fixed then alpha for in this value with a very small coupling constant. That what I mentioned previously was that this alpha were important, and it's because this value for alpha is exactly in the right ballpark for the one beta function coefficient that would appear in an SU theory of a D7 brane. So we can then associate this parameter alpha of these logarithmic definitions as associated to the one loop function of this D7 brane. So by borrowing this parameter alpha, what we found is that we can find anti-de Sitter, Minkowski, or de Sitter, depending on the values, as we can see in the plot. As we can see in the plot. Okay. So, okay, we managed to solve the case of stabilizing moduli at late time, but now how we introduce inflation, which was the main objective of this talk. So then we consider the standard type 2B string theory compactification from a Calabi-Yau stringfold in the presence of fluxes. So then we introduce, as I mentioned, the system of a brane and an anti-D3 brane. So we imagine a Calabi-Yau manifold in which we have cycles wrapping, branes wrapped in cycles, sorry. And in the theory of the throat, we have an anti-D3 brane. And in the throat, we have a D3 brane. So the potential that is gonna tell us about the interaction between the brane and the anti-D3 brane is this one that appears here. And however, a very useful framework in order to study this system is called the nilpotent superfield framework. And in this case, in order to mimic the behavior, the dynamics of this brane and this brane, we consider then the nonlinear supersymmetry that appears with Agostino's superfield X. And this is going to be the responsible of breaking supersymmetry. And then we also have our Keller modulus and the inflaton. That's going to be, as I mentioned in the beginning, it's going to be mediating the separation between the D3 brane and the anti-D3 brane. So the most general Keller potential and superpotential that we have for this theory is in this form. So something that is very important to notice here is that now the physical Calabi-Yau volume is not gonna be tau, but instead it's gonna be tau plus this correction, let's say correction coming from the separation between the brane and the anti-brane, and this is precisely the one that is gonna be stabilized in the end during inflation, and is gonna cause the absence of the eta problem. So the corresponding scalar potential for this case, for this form of the scalar and the superpotential is in this form. And again, we can notice that at tree level, in which we have F that appears here equal to sigma, so we don't have corrections that I mentioned in the beginning. And also this is 0, and this is just 1. We recover this expression for the scalar potential, sorry, for the scalar potential, which if we associate this W with the work factor, can be identified with the anti-brane contribution for the uplifting. So we can divide the study then of this scalar potential in the case in which we have present this G or we don't have it. So let's consider first the case in which we have this scale, this linear factor here. So with the linear term included here, what we're going to have is a perfect square actually for the scalar potential, which is very interesting. And we found that this perfect square form of the scalar potential admits a Minkowski minimum at this value for the minimum and for an exponentially, for this value for the sigma, for the minimum of the volume. And however, since we have Minkowski, but we want the zeta to have inflation, we need to introduce the perturbative corrections to the first term, the f, the function that appeared in the scalar potential. So in order to know what are the relevant corrections in this case, we need to understand how to connect in some way the inflationary potential with the late time potential. So what happens then is that once inflation finishes, we have the brane getting closer to the anti-brane, such that at some point they will annihilate and the scalar potential will vanish, as we can as we expect. So, however, the volume modulus will have to relax to go to the post-inflationary minimum in order to avoid the compactification. So, in order to avoid this compactification, what we have to impose then is that the maximum of the late time volume modulus has to be larger than the minimum of the early time volume modulus or the volume modulus of inflation. So in this case, the leading order perturbative corrections are the alpha prime cube corrections, such that F is going to look in this way. So we have the BBHL term here then as the correction. And this implies that now the scalar potential is going to look like this. And if we expanded this for large field values, we found that we can write it again as now the power law, the inverse power law, with n equals 4, which is what we expected if this is the brane-antibrane potential. So just to be pictorially more clear, we can say that we plot here, in this case, the potential that we obtain without with just the leading order terms in blue, which is, as I mentioned, a Minkowski minimum. Then when we introduce the corrections, the leading order to the next two leading order corrections, we can obtain the zeta. And just plotting now the minimum that we obtain with during the inflationary period and compared with the late time potential, we see that there's a field displacement from one minimum to the other one. And in this case, in particular case, for the values that we use to plot, we have a Planckian distance excursion or a Planckian portion of the volume modulus. However, this can also be for larger values of the flank mass. So now what happens in the case in which we don't have a linear term? So in this case, as we saw, we just have this case that corresponds to the anti-brane. So we added this to the potential, and however, we have still to stabilize the volume modulus. So we added the corrections to this function f in order to stabilize the volume modulus, which results in having this form of the scalar potential. So in the end, this also reproduces this form of the inflationary potential, but now the volume modulus is stabilized with pure perturbative corrections, which is in the end what allows not having the eta problem. And similarly to the previous case with the linear term, here we also found an inflationary potential. But in this case, what we found is that the inflationary potential and the late time potential are like basically in the same region. So we have a very, very close inflationary potential to the late time potential. And just finally, in order to yes.
Sorry, can I just ask a question about the V? I've only been tuning in and out, so I apologize if you said this already. The WX, that's non-perturbative, or what's WX, W sub X here?
W sub X is the term of support potential that has to do with the nilpotent superfield level spin, like the derivative of this.
So a brane-antibrane contribution to the potential itself. So there's no instanton correction at all to your V?
Oh yeah, no. We are only considering pure perturbative corrections. We are not considering non-perturbative effects. Yeah.
So what's making the space big? Maybe big enough to trust perturbative alpha prime expansion?
Sorry, can you repeat the question?
So naively, if you're balancing perturbative corrections against each other to get to a minimum, the space should be of order L string, roughly. I mean, it should be something small, relatively small, where you wouldn't have been able to neglect higher order corrections. What's making this control, I should say?
Well, I'm not sure if you understand the question, but we consider
like if you're balancing like one loop, I mean, if you're balancing like one loop against two loop or tree level against one loop, typically the minimum is at a size of order, the size of the orders L string. So normally you would expect that to be out of control unless there's some extra parameter that makes the volume big. What makes the volume big of the compactification space?
I mean, we're finding here that the minimum is at large values. We are finding that this is consistent with the EFT. So we are asking well, we're finding that we can find a minimum in large for large V and small GS. I'm not sure. Sorry, I'm not sure if I understand the question.
Maybe I'll ask again when you're close to wrapping up. So maybe I should ask again once you're wrapped up.
Perfect. Yeah. Okay. Thank you. So just especially just to finalize, there are some EFT bounds that we have to consider in order to make sure that we have a consistently effective field theory. So one of them, for example, is that the D3 brane is in the throat, which imposes the first condition. Then we have that the gravitational mass must be below the warp string scale in order to not have massive states. And we also have the dilute flux approximation, the curvature corrections under control, and this conical modulus stability condition. So we impose these conditions in order to find what are the correct values for, or what are the appropriate values for GS, K, and W0, which are the three parameters that we have that we can tune. And we found that we can find a large region for the case in which we consider linear contributions, and also without including these linear contributions, we find a smaller region but still a region in which we still can satisfy all these conditions and we still have the zeta minimum. So now that we know that we have a consistent EFT, we need to compare this with experimental results. So, oh, sorry. Well, this plot we're just mentioning. We are also imposing that apart from these EFT constraints, we also have to match with the inflationary observables, such as the scalar tensor ratio, the NS, and so on. So this plot are already considering that we match these observables. So just as a summary, what we did here is focus in this brane-antibrane inflationary model. Then we follow some of the steps of KKLMMT by introducing warping in order to obtain a flat potential. But now the difference here, the main difference is that we didn't use non-perturbative correction to stabilize the volume modulus, but instead just pure perturbative corrections. And so in this way, we managed to avoid the eta-problem. And also, we use the nilpotent superfield formalism to describe the D3 and the D3 brane system in terms of this nilpotent superfield. And we saw that including a linear dependence of this scalar potential on X, we discovered a new perfect square structure, which in the end can get inflation from Minkowski by uplifting this Minkowski minimum by adding subdominant alpha prime corrections. And also in the case without this linear term, we also show that by exploiting this logarithmic modular redefinitions, we can also obtain the zeta in the end. So as I mentioned in the end of the talk, like by the end of the talk, like imposing the observations and consistency conditions of the FT, we managed to reproduce the enough e-foldings, the right amplitude and spectral index of scalar fluctuations and the tensor-to-scalar ratio. All of this consistent. So just I think the most important things for future work is like to study precisely what happens in the end of inflation, which usually can be understood by terms of what is called a tachyonic waterfall, in which a tachyon has this waterfall in which it decays in different particles. And yeah, which is what is expected usually when you have a brane-antibrane inflation. But I would say that most importantly, we need to realize a concrete implementation or a concrete realization of this, particularly a Calabi-Yau-oriented compactification that would allow us to reproduce these values for GS and W0 in this region of the parameter space. So I think that this can be summarized as we have to embed brane-antibrane inflation in a globally consistent Calabi-Yau compactification. Yes, well, that's all. Thank you very much. And please, if you have any question, let me know.
All right, thank you, Mario, for the very nice talk. It looks like we have some questions from the audience. I think starting with Vincent.
Yes, thanks, Mario. So I was wondering the following, you rely on these additional corrections to stabilize your moduli, but in what sense do you know that the next corrections are not important? Why don't you have a Stein-Seibert problem in this case?
Yes, that's a very good question, and it's not that they're not important. We actually consider all the next to leading order corrections that I mentioned in the beginning that are the all known corrections. And what we found is that when we actually compute we do the same study, it modifies the story, but not qualitatively. Sorry, only qualitatively, because it's the minimum just kind of shifts a minimum, just a very small amount. So in the end, it doesn't change the results. So we consider all the corrections. So we don't have a problem with that. So and that is very important to mention that we actually take took into account all these non-perturbative corrections that are computed so far.
Yeah, but maybe corrections that are not computed yet could change the story, no? Isn't that a worry?
Well, in principle it might be, but we don't know it. So we could speculate that there might be one that can appear, but this is also something that would happen in other scenarios as well, in which they consider perturbative corrections. So in the end, we only can say something for sure for the corrections that we know.
Okay, thank you.
So we also, I want to point out, have time for after the talks for discussions. Oh, we have, I guess, Artur, Tom, and Sav raising their hands. Could these be short questions and short answers, please? Or
okay, I will try to be
maybe
very
Artur
short.
first.
Yeah, very brief question. So what about the slow roll condition? So I remember from looking at this many years ago that it's basically the Dvali-Tai model. You have a brane-antibrane potential, and it's simply too steep. No matter what you do, the Calabi-Yau is too small to have enough distance to get slow roll. I assume that you somehow solve it using warping, but I didn't understand that, because it seems to me that you have warped down the potential, but not the offset. I mean, the offset meaning the energy which is released when the branes eventually annihilate. So I'm somehow puzzled how exactly that works. I mean, can you explain where the slow roll comes in, given that this doesn't usually work for brane-antibrane inflation?
Well, I think that this is also what it was done actually from KKLMMT. They just by introducing the warping, they managed to get the proper value for to get a flat enough potential just by introducing the warping. So we just did precisely.
KKLMMT used they used the fine tuning of the inflection point. That's a different story. In your potential, I didn't see the warp factor come in. You simply had a clean polar potential, right? 1/r⁴. That suggests that you simply skipped the whole potential.
No, we actually have the warping here. Just let me find it. So, for example, here basically the warping will be coming. As I mentioned here, we can associate the contribution for the warping or from the warping coming in this term, this WX.
No,
so in the end,
the potential is higher. Sorry, you have a second line. You have interbrane potential. There's only 1r in the second line.
Yeah.
Yeah. Where's the warp factor?
warping comes here. Yeah.
But if you suppress the whole potential, it doesn't change the slow roll condition. Just making the whole potential smaller will not buy you slow roll if you didn't have slow roll originally, right? Multiplying the potential by small numbers. You need, I think you have an extra warp factor in front of the 1/r⁴ term, but then there is one out front somehow. That I didn't understand. Why there's a warp factor for one term, not for the other. Okay, maybe that's too detailed. I don't want to delay too much. Okay.
Okay.
So, in the interest of time, Tom and Sav, would you be okay with postponing your question until after the next talk? Thank you. Okay, let's thank Mario again for the nice talk. Thank you, Mario.